So this demo is going to render a buffer full of points. In this case, there are two arrays. There is an array of points and there's an array of colors. OpenGL will read 1.1 color as it goes through. You can also now see that we're viewing this as a 3D rendering as well. So this uses the same basic setup as we've done previously, that we've got our setup here for setting up our OpenGL version. So call profile OpenGL here. As you'll notice here, we've got a parser to parse command line arguments. So I can default the number of points there, so it's 10,000 points there. We can run this again when we get started here, so I can basically minus P10 and it'll run with 10 points, as you can see there. Or I can ask it to do many more, and it will do many more, as you can see there. As you can see, that's getting a bit slower there now. We're struggling to render that many points, but it's still working. Do a smaller amount there, you can see it's doing quite well. And obviously we've got the debug as well. So again, this is using the overall OpenGL window, so that's exactly the same as the previous demo. What we're also using now, and if you've watched the previous video, we're using the NCCA NGL library, and from that I've imported the Map4, the shader library, the Vec3, Lookat and Perspective, and I'll be explaining those as we go through. So again, number of points is passed in as a command line argument here. Initialized GL is called once when the window is first about to render, and this will do our basic setup. Now in this case, setting the clear color, depth testing and multi-sampling as before. First thing we're going to do is we're going to use the NGL library to load in our shader. It has a very convenient built-in function here called load shader. It takes in two strings, so basically the string is the name of the shader, the path of the vertex shader, the fragment shader, optionally a geo shader. So my shaders here are in text files now rather than being in just strings as before. And as you can see here, I've got a layout with the first input being a Vec3 of our input position, the layout being a Vec3, so layout 1 as Vec3 input color. Very similar to the first triangle one that we did. I've got this extra parameter here now, which is MVP, and MVP is being used here to take the input position and multiply it by this modeling, viewing and projection matrix. This is calculated in the program itself and passed in once per frame to allow us to render all of the points with this one matrix. And this is quite common, that we set up this transformation per mesh or per group of meshes in this case, well, group of primitives to render. And then the color is just passed through and the fragment shader just sets the color there. So it's quite simple. We are activating that shader, so shader lib use, point shader, that's the name of the shader I've generated there. I've activated this once, that will stay as the currently active shader all the way through the program, so it's relatively simple in OpenGL to do that if you've only got one shader. Then I'm calling this create points method. So this is twofold. The first thing it's going to do is going to generate our data, then it's going to create our vertex array object and our buffers for the data. So generate the vertex array here, so it's generating one vertex array, binding it. All subsequent buffer operations will now happen on that bound buffer. I'm using MP random to generate me a single buffer of points in the range of -4 to 4. I want this many by 3, and I want them as an MP32 float. So basically generate me a range of floats within that range, and I'm doing the same for the colors. but I'm generating it between the range of 0 and 1, which is going to represent the RGB components. Unlike previously where I had a single buffer, now I'm generating 2 buffers, because what I'm doing is I'm creating a buffer for colors and a buffer for the vertex data for the points. So I'm generating this. That will generate 2 IDs, and I'm binding the first ID. I'm copying the buffer data across. Notice I'm using points.nbytes, so that just happens directly as bytes from that NumPy array. And then I'm setting here my vertex attribute pointer. So it's saying input 0 has 3 components of type float. No need to normalize. It starts at the beginning of the array. That's what that 0 indicates. And there's no offset. Basically, if we put none in here, the data is contiguous. And this is nice and easy to set up these multi-buffers. And when we issue a draw command, basically we'll just read 1 by 1 by 1 by 1 as we go through the data for points. So the same is true here for my color buffer. Obviously I'm binding the second array because this is a new buffer. Passing in the color data, I'm saying that's on input 1, 3 components of type float. Start at the beginning of the array, and there is no offset, therefore the data is contiguous. When I paint, I'm going through here. Now I'm doing a little bit of matrix maths here. So all I've got here is my rotate in Y. So the map4 class has a rotate Y method. What rotate Y does is it generates a 4x4 transformation matrix, calculating basically the cos, sine, cos rotation matrix for a rotational around the y-axis. And then I'm combining the projection, the view, and then this, if we assume it's the modeling, so this is the modeling, viewing and projection matrix combined together to give us MVP. And this function set uniform will look for the uniform on the shader and set it. What happens under the hood with the shader library is when the shader is compiled, it will go off and create a global dictionary for the shaders and for the uniforms. And when we say set uniform, it looks up the ID of that particular uniform, and then it will call the relevant code under the hood to set that value. So I've abstracted away all of the complex stuff by managing it in the shader lib. You can look at the source code online for that. Setting the point size. Now this is something other graphics APIs tend not to have. So by default, when we run this, I think the point size is set to something about 4. That is the point size of 1. OpenGL will rasterize our points between a range, and as you can see, we can make these bigger and bigger and bigger. Generally they go up to about a maximum size of 128 square, which is actually very useful because you can render textures to these and other things as well. So it's quite a useful feature being able to do that. And as you can see, as we get smaller, we go down, and a point will be a single pixel in that case. And that's in fact what the other graphics APIs will do. They don't have this feature of a GL point size. Finally, bind our vertex array, draw it, and we say start at the beginning of the buffer, and this is the number of points. And in this case, we're rendering as points, so GL points. We go GL lines, for example, and run that. We'll get a series of lines. Again, GL line loop. We'll get one line that's all connected together, and then go back to the beginning. We can also GL triangles and render a polygon soup of triangles, as you can see there, and so on. So it's again, OpenGL is fairly easy in this perspective that we can quite easily go in and change these things, and it's not part of the fixed pipeline as it is in the other elements. The only other thing here, when we resize our window, this will call the perspective to rechange this perspective function. So I've got it set to 45 here. If we make it narrower like that, you can see we're closer. And if we make it bigger like that, things zoom further away and so on. So that's the sort of field of view of our projection. We will go through the mathematics of this in a lecture at a future date. The one thing here you'll notice I've got ratio set to 1, and the reason for that is, for this purposes of this demo, I'm on a second monitor and it doesn't pick up the aspect device ratio until I resize explicitly there, which is annoying, and I can't figure quite out a way to do that. So that's the points demo, relatively simple. We start a timer as well, actually I forgot to mention that. So you'll notice here, self.start timer, that starts the timer, and then every frame that timer will trigger the timer event. In this case is adding 0.5 to the rotation, and then calling update, which triggers the redraw. What we could do is change that somewhere else. So for example, if I set that to 0, now you can see it's rotating incredibly quickly because I've got my rotation going a lot faster. But then again, what we could do is go through and take into account that rotation value. Still a lot quicker because it's basically forcing updates all the time, and it's quite quick to do that. We would be better off generally calculating some sort of DT update on how long the time takes between frames and then proportionally update. But again, more of that in a future lecture when we get to that stage.